Okay, now your textbook has talked about four specific cases: the isobaric, adiabatic, isothermal, and isovolumetric. And now we're getting into the general case. I've already kind of given you an equation for the general case. I want to make sure that parentheses is in there. Um, but basically it's this. Um, and I could make a couple of notes about the degrees of freedom, just to, let's see. Namely that the specific heat at constant volume is degrees of freedom over 2 times R. So we could solve for degrees of freedom over 2 is C sub V over R. So if you had a gas, instead of knowing the degrees of freedom, but you had a gas where you knew the specific heat at constant volume, you could replace that degrees of freedom over 2 with C sub V over R. But this is a general case of our relationship. So we have a quantity of 4 moles of a monatomic ideal gas, so degrees of freedom is 3, expanding from 0.1 meters cubed to a final volume of 0.3 meters cubed. And it doesn't say in the problem, but it shows in the graph that it starts at, I guess, at atmospheric pressure to 250,000 pascals. And we want to compute A, the work done on the gas, B, the change in internal energy of the gas, and C, the thermal energy transferred to the gas. So some of the things that I could figure out at this point, I could figure out delta PV by saying 0.3 times 2.5, or 0.3, or what is it, times 250,000 minus 0.1 times 100,000. That's probably the easiest way to get the delta U by finding change in PV. We could also find delta T. We could find T initial and T final, because T initial and T final are going to be equal to P initial, V initial over NR and P final, V final. Sorry, V final over NR. So we could find T initial and T final. And finally, we can find the work done shrinking the gas by taking the negative area under that curve. So I think this way looks like the easiest to get delta U. It's going to be 3 halves times delta PV, so I'm going to take this and multiply by 3 halves. And I got 97,500 joules. I could have found the initial temperature was 301 Kelvin and the final temperature was 2260 Kelvin based on those pressures and volumes. That's what they did in the text. And then find that delta U is equal to 4 moles times our C sub V is 1.5 times 8.31 is about 12.5, and then multiply by that change in temperature, which is delta T is 1960 Kelvin, and that comes out to be 98,000, which two significant digits is about the same as 97,500. So 2 different ways of coming to that answer. I think this way is quite a bit simpler. Now, as for the work, you can see from the diagram that we have a rectangle and a triangle under the PV curve. And so here I'm going to take the area of the rectangle plus the area of the triangle. And since the arrow is moving to the right, this is work of growing or work on the environment. So work shrink is going to be negative of, and I didn't give myself room, 100,000 times 0.2 plus 0.5 times 200,000 times 0.2. The area of the rectangle plus the area of the triangle. I'll tell you, I never seem to get these areas right. Okay, pressure final is 2.5 E5. So from 1 to 2.5, this should have been 1.5 E5 or 150,000. So the total comes out to be negative 35,000. So then we can say delta U equals Q plus W, delta U equals Q plus W, and we have delta U was 97,500 equals our Q minus 35,000. So our Q has to be equal to 132,500 joules. So now we have answer to part A, which is the area under the curve, the answer to part B, which I found twice, once by doing delta PV and once by doing NR delta T, or NC sub V delta T, sorry. And finally I found the heat by subtracting the two, or adding the two values together. In the remarks, they're calling this an exotic cycle. It's not one of our four main ones. It is kind of unusual to have pressure and volume increasing at the same time. There's kind of a strange phenomenon must be going on for that. They say it's usually necessary to use calculus to find the work, and in this case, the work is the integral of the PV curve. Just to point out, though, that doing the area under the curve here was fairly easy. I'm kind of going through this while I paused the video. I was thinking, how would you do this with calculus? Well, first you need to find an equation for the pressure PV curve, which involves finding a linear relationship. The slope is equal to P minus initial P divided by V minus initial V. And you can solve for that for P, and you get P equals 750,000 V plus 25K. And then you want to integrate that with respect to the volume, which is going to be taking the integral of V dV times 750,000 plus the integral of dV times 25,000, which would be 0.3 squared minus 0.1 squared over 2 times 750,000 plus 0.3 minus 0.1 times 25,000. And you should get the same result from that. But, and yes, after plugging it into the calculator, I did get 35,000 joules for the work on the environment, just as I had up here, negative 35,000 joules for the work of shrinking. But you can see that doing it as the area under the curve is actually quite a bit easier than the calculus form, because first you have to actually find the line. You have to find the equation for that line, pressure as a function of volume to use the calculus. The other part of this remark is note that the solution to part B could have been facilitated by yet another application of PV equals nRT, and that is actually what I did. I did 3/2 delta PV, and that we did not need to know the number of moles or the temperatures, and we just needed to know the initial and final pressures and volumes. Okay, question 12.9. For a curve with lower pressures but the same endpoints as in figure 12.9a, would the thermal energy transferred be smaller, equal to, or greater than the thermal energy of the straight line path? So in our PV diagram, we have a straight line path, initial and final, and you're going that way. And we want to consider something with a lower pressure but the same endpoint. So something maybe like this, or even like this. So we can say in regarding this that work of growing or work on the environment is for the low curve is less than work environment of straight curve. And we can also say the delta U is the same. So if we say Q is equal to delta U, and this is plus the work on the environment, usually we say delta U equals Q plus the work on the gas, but this I'm reversing it. So since the work done on the environment is less in this case, we can also say the heat exchange is less. I'm just going to say Q is less at lower pressure. The work on the environment is less at lower pressure, and the heat is less at lower pressure. And that's kind of a pressure, a principle of all of the engine cycles, that the gas does the work at high pressure and then it's compressed at low pressure. So you end up getting work out of it by having the work done by the gas at high pressure and the work done on the gas at low pressure. So this associated exercise just asks us to find the W, U, and Q, W, delta U, and Q for this diagram. And we can say that the work is done on an expanding gas. So we can say a work environment is equal to the area under that cube. It looks like it is a rectangle with 0.1 by 100,000 pascals plus a triangle of 0.1 by 300,000. So our work on the environment is 25,000 joules, or the work on the gas is negative 25,000 joules. Next, let's find out what delta U is, which is we said it was a monatomic gas, so it is 3/2 times delta PV, which is going to be, okay, final minus initial is 0.2 times 100K minus initial is 0.1 times 300K. and that comes out to minus 10,000 joules. And finally, our heat is equal to the delta U plus the work on the environment, which is going to be minus 10 kilojoules, and the work on the environment is positive 25 kilojoules. So it's going to be positive 15 kilojoules. Now, as I already mentioned earlier in this video, I am terrible, absolutely terrible, at calculating areas under curves. So what is the height of this triangle? The top is at 3, the bottom is at 1. This should have been 200,000 pascals, not 300,000 pascals. And then I forgot to multiply this by 3/2, and that should have been minus 15,000 joules. And our heat then should have been delta U minus 20,000, minus 15,000, plus work on the environment, which was positive 20,000. So that Q equals 5,000 joules. So I made 2 blunders when I worked through it the first time. I calculated the height of that triangle incorrectly, and I didn't carry through that degrees of freedom over 2 in this calculation. But once I fix those things, I have the answer that they have. Yay! Okay. And finally, they wrap up section 12.3 with table 12.2, and I have given you a much larger table which contains all of the information from table 12.2 and some additional information as well. So with all that in mind about the pressure and volume, I've added a little bit more to my table so that we have a change in PV under the adiabatic expression, a P delta V under the isobaric, and a V delta P under the isovolumetric column for delta U. So I will upload that and replace the current document with this one that's been a little bit corrected and a little more information has been added to the table.